Welcome to Brain Vision.
Hi everyone, so what we have is steam that is going through a condenser, and that condenser is cooling the steam through water that is pulled from an outside source. So steam is entering and exiting this condenser at a temperature of 50 degrees Celsius, and our cooling water is entering somewhere between 10 and 20 degrees Celsius. We're asked to vary that, and it's exiting at a temperature of 27 degrees Celsius. The m dot of this cooling water is 101 kilograms a second, and what we're asked to find is the rate of steam condensation as we change the inlet temperature of the cooling water. So the first thing we're going to do is go ahead and write down our assumptions. We're going to assume that this is a steady state process, so things are not going to be changing with time. We're going to also assume that all of the heat transfer that comes out of the hot fluid is going into the cold fluid. So that basically means that Q hot is equal to negative Q cold. And we're also going to assume that any changes in potential and any changes in kinetic energy, as well as any work, is going to be negligible. And we're going to assume that all of these fluid properties are constant. So fluid properties are constant. So what we'll go ahead and do is write down our energy balance. So we know that the energy coming in minus the energy leaving is equal to the change in energy of our system. And our system is defined as the cold water tubes in the system. So we're assuming that it is a steady state problem. So we're going to go ahead and say that the change in energy of the system is equal to 0. Therefore, the change in energy coming in, or the energy coming in, is equal to the energy that's leaving. Now, what we can do is actually go ahead and look at the properties of water as well. So the heat of vaporization of water at 50 degrees C, so our HFG, will be equal to 2,382 kilojoules per kilogram. And our specific heat of water is equal to 4.18 kilojoules per kilogram degree C. So by taking the energy balance that we have, what we can say is that the heat coming in to the cold water tubes plus the incoming enthalpy of the cold water is equal to the exiting enthalpy times the mass. What we can actually do is solve for Q out or Q in, so that Q in is equal to m dot H2 minus H1, and using the definition of enthalpy using temperature and specific heat, we can say that m dot Cp T2 minus T1 is equal to our Q dot in. Now, as we said before, all of the heat that is gained by the cooling water is equally lost by the steam. So what we can say is that this Q dot in is equal to m dot times HFG of the steam. So all of these are steam components. So we can solve for m dot of the steam by saying that m dot steam is equal to Q dot in all over HFG of the steam. So if we plug in for Q dot, we can say that Q dot is equal to m dot of the cooling water times Cp times T2 minus T1 all over HFG, and this is equal to m dot steam, and that is our rate of condensation. So as you can see, we now have m dot in terms of all known quantities except for T2, which is the except for T1, which is our inlet temperature of our cooling water, which is what we're changing. So by changing this term, we can see in this graph here that as we increase the cooling water temperature at our inlet, as shown on the x-axis, we have the rate of condensation on the y-axis. We see that there's a decrease. As the cooling water temperature increases, the rate of condensation decreases. And this makes sense because we have hotter water and we're able to pull out less heat. So that is our final answer.